Hello my friends and welcome back to the You Can Do TV channel. Prefabricated rebar cages are installed to stay rigid under lift, and this video documents the placement phase of prefab reinforcement, assembled in the yard and lifted into position by an 80-ton rough terrain crane. The cage is prepared with added stiffeners to control deformation and avoid yielding during hoisting. Equal angle steel reinforcements are fixed to the vertical main bars, creating stable lifting points before the load leaves the ground. That setup already feels like insurance against unwanted flex. During lifting, load balance is adjusted through chain blocks connected via H-steel supports, preventing uneven force at suspension points. Height is fine-tuned mid-air so alignment stays true as the rebar settles into its designated location. Seeing steel behave this calmly while hanging says a lot about the prep. Final positioning confirms bar spacing and orientation before release. Simple moves, but no room for guesswork when gravity is fully involved. An arch stretching 384 meters anchors the Almonte Viaduct on Spain's high-speed rail line. Construction advances through staged arch erection, temporary cable support, and controlled lifting of towers and deck segments. That scale hits fast. Real-time monitoring tracks structural response as sections close the span. One misread here would snowball. The completed viaduct secures record-span performance while keeping alignment steady for Madrid-Extremadura trains under high-speed railway load demands today. Steel pile cage assembly sets the foundation long before concrete ever enters the ground. In this deep foundation operation, steel bars are cut, sorted, and positioned to form a cylindrical reinforcement cage designed to resist axial and lateral loads. Longitudinal bars are aligned first, establishing the pile's main load path. Circular ties are then placed at defined spacing, locking the geometry in place and preventing deformation during handling. That spacing is doing more work than it seems. Mechanical fastening secures intersections, ensuring the cage maintains its shape during lifting and lowering. Lifting points are integrated into the structure to allow safe vertical handling. A cage that twists here would cause trouble later. Once assembled, the steel pile cage is checked for diameter, length, and straightness before being lowered into the drilled shaft. This is the moment where preparation quietly pays off. The cage is positioned to maintain concrete cover, ready for the pour that completes the deep foundation system. A breakwater only works when every unit locks the C in place, and that challenge defines the Acropod units built for the dig of Cerberus. Production focuses on casting complex concrete shapes that rely on geometry rather than mass. Molds are prepared and reinforced, then filled to achieve consistent density across each arm and node. Those edges aren't decorative at all. After curing, units are demolded and inspected to confirm balance and surface integrity before transport. On-site, cranes position each Acropod following a precise placement plan that controls interlocking and void ratio. One wrong orientation and the whole layer loses grip. Divers verify seating underwater while operators adjust lifts to maintain alignment along the breakwater face. Layer by layer, the structure builds resistance against wave energy without relying on heavy rock armor. Seeing concrete behave like a puzzle piece never gets expected. The Rebar dig advances through coordinated casting, handling, and marine installation, supported by dredging, electrical works, and underwater operations. Real conditions, storms included, test every decision. That moment when a unit settles cleanly says everything. By the end, the Breakwater delivers long-term coastal protection through controlled geometry, not brute force, shaped by teamwork across specialized trades. Remote terrain shapes every decision during the construction of Lagerway wind turbines in Finland. Civil works prepare foundations under harsh conditions, creating stable bases before tower components arrive. The MST tower system allows ground-level access, reducing climbing exposure during installation. Tower sections are lifted and connected in sequence, keeping alignment consistent as height increases. That access system quietly changes how fast crews can move. Nacelles are positioned next, integrating drivetrain and control systems already tested off-site. Rotor hubs and blades follow, lifted individually and secured with controlled positioning. Seeing blades settle into place never feels routine. Logistics play a central role, with turbine components delivered in phases to match installation windows. 5 complete turbines reach the site first, while additional units follow through the winter months. Timing matters more than raw lifting power here. Installation progresses efficiently, completing each turbine within weeks. The project ultimately forms 2 wind parks with a combined capacity of 27.5 megawatts. Proving that planning keeps progress steady even in extreme conditions. Mechanical concrete TDC nailing keeps everything fixed so compaction can move forward without rework. Gravel spreads across rows of tire-derived cylinders as a loader advances. That steady base saves time when the next pass rolls in. Rising toward the 100-meter mark, the Yusufeli dam body reflects the scale of concrete work shaping Turkey's highest dam project. On-site, steel reinforcement frameworks are positioned and fixed to define each structural segment. Formwork panels are assembled to guide placement while maintaining alignment across the dam face. Concrete delivery follows a controlled sequence, filling sections layer by layer to build mass and stability. Seeing this much material placed without interruption really changes how you think about scale. As pours continue, crews coordinate timing to keep joints consistent between lifts. Embedded components are set during placement, locking functional elements directly into the structure. That coordination has to stay sharp, or the whole schedule slips fast. As the dam body climbs, surface treatments are applied to exposed areas to maintain uniformity. Monitoring teams track height progress as the structure passes the 100-meter level. Hard to ignore how steady the pace feels, even with so many moving parts. The volume of concrete now exceeds 1 million cubic meters, reflecting sustained output rather than a single push. Feels like every pour quietly adds weight to the valley itself. Each completed stage strengthens the body, preparing it for the next rise in elevation. Vertical access changes everything when a mine goes deeper. Shaft sinking in the Woodsmith project pushes straight down, opening a controlled path through layers that refuse to cooperate. The work advances by lowering crews and equipment into a circular shaft, where drilling patterns mark out each cut. Broken material is hoisted away while the walls are stabilized in stages to prevent movement. That moment when the shaft stays clean after a blast feels like a small win underground. As depth increases, lining systems are installed to hold geometry and protect long-term operation. Services follow close behind, with ventilation, power, and guidance systems adjusted as the shaft extends. Timing matters here. Each task has to clear before the next can move in. Miss the window and everything stacks up fast. Heavy lifting cycles repeat, lowering rings, setting them true, then locking them into place before descent resumes. Progress is measured in meters, not speed. There's real tension when the cage drops again and the walls don't budge. Step by step, the shaft becomes a permanent gateway, built to support decades of mining below the surface. Concrete caissons reaching 26 meters high are prefabricated step by step at the Nador West Med Port in Morocco. At the prefabrication zone in Yazene Bouafar, 2 production lines operate independently, allowing parallel caisson construction without downtime. Steel reinforcement is placed for the base slab, followed by concrete pouring that locks the foundation into a single rigid mass. That slab already carries the weight of everything that follows. Once cured, the caisson moves from stage 1 to stage 2 for slipform setup. The sliding formwork system is lowered and prepared, allowing the vertical walls to rise without stopping. Reinforcement placement and concrete pouring continue non-stop, running 24 hours a day for 5 to 6 days, depending on concrete setting behavior. No pauses here, because stopping mid-wall would mean structural trouble later. The slipform steadily climbs as fresh concrete gains strength below, shaping walls that reach up to 26 meters high. When prefabrication is complete, the caisson can measure up to 20 meters wide and 30 meters long. It's then transferred from stage 2 toward the installation phase. A transport barge docks carefully, aligning with the caisson before loading begins. Seeing that alignment click into place feels like threading a needle the size of a building. The caisson is moved onto a semi-submersible barge and prepared for launch. Ballast tanks flood, allowing the structure to float free. Tugboats guide it toward its final position along the breakwater. Once aligned, ballast water is released to stabilize the barge, leaving the caisson ready for final placement and superstructure installation. At this scale, gravity does most of the work, and there's no room for second tries. "50 meters across and rising higher than a city block, the aquadome is lifted as a single glass and steel structure onto Icon of the Seas. The 363-ton component is guided slowly into position, turning scale into a coordination challenge rather than brute force. This lift shows how marine construction depends on planning more than muscle. The operation stretches over 80 hours, with alignment checks repeating at every stage. Seeing such a massive structure settle perfectly feels unreal for a second. Once secured, the aquadome becomes a defining space on the ship. Every pause during the lift matters as much as the motion itself. Panel edges align before the crane fully releases, showing how precast wall installation relies on accuracy rather than force. Each wall panel arrives with lifting points positioned to control balance during hoisting. The panel is guided into place slowly, matching anchors cast into the foundation. That moment when the panel hovers just above its seat always tightens attention. Temporary braces hold the wall steady while final positioning is checked. Adjustments are small, deliberate, and made through measured pulls rather than pushing. This step decides whether the next panels will cooperate or fight back later. Once vertical alignment is confirmed, mechanical connections secure the panel to the slab and neighboring elements. Grout is placed to lock loads into the structure. You can feel the site relax once the first panel stands on its own. Subsequent panels follow the same logic, forming straight lines and clean corners. Precast work rewards patience more than speed. As the walls connect, the building footprint becomes readable. That shift from empty slab to defined space happens fast. HDPE pipelines don't forgive sloppy joints, especially inside a tight gallery like Mont Alban. This mirror welding operation focuses on joining PEHD conduits using controlled heat, pressure, and timing. Pipes are aligned in jaws. Then a facing tool trims the ends until contact lines match cleanly. If alignment drifts here, everything downstream pays for it. A heated mirror plate moves in, holding steady at 200 to 220 degrees while both pipe faces warm for 90 seconds, then fuse for 10 minutes. The plate withdraws and hydraulic rams push the sections together at 75 bars. That slow push looks simple, but it decides the joint's future. Cooling takes over an hour before the line advances into the narrow tunnel. Space stays unforgiving, movement stays measured. You can feel the tension when the weld locks in. Gorelli and Suez crews handle the replacement for Regio d'Azur, while trainees Kevin and Joey learn hands-on. One solid joint here means fewer sleepless nights later. Pressure ratings rise to 10 bars once the new line runs safely installed.
Driving a new pipeline under Tennessee soil relies on the steady force of the Robbins small boring unit paired with the auger boring machine. Their combined setup pushes through packed ground with controlled torque, moving the project forward without open-cut trenches. The punch behind each rotation might surprise you. The cutter head on the SBU-A fractures the material, while the ABM's auger flights pull debris back through the casing. Kind of feels like the ground is giving way to a giant pencil sharpener. Sections of pipe follow behind, aligned as the bore advances. Some viewers might react the moment the cutter breaks through the final layer. The result is a clean path ready for utility installation.
Every load mixed on the AUSA X1100RH is built to move fast and stay independent. This self-loading concrete mixer handles material intake, mixing, and delivery in one compact machine, cutting out delays that usually slow small pours. The front-mounted bucket scoops aggregate directly from the pile, lifting it into the drum without support equipment. From there, cement and water are added, and the drum rotates to blend the mix evenly. Mixing takes only a few minutes, keeping momentum steady on site. That turnaround feels quicker than most setups you'd expect for this volume. Each cycle delivers up to 1.1 cubic meters, sized for frequent, controlled pours rather than oversized batches. The operator drives straight to placement, tipping the drum to discharge precisely where needed. That direct move saves more time than it first appears. By removing truck coordination and waiting windows, the X1100RH reduces idle costs and keeps work flowing. Two models offer flexibility depending on site needs. This setup feels like it refuses to waste time, turning short mixes into consistent progress. What makes a marble block finally give way inside the billet quarry without blasting it apart? This operation relies on leverage, timing, and machines working in sequence rather than brute shock. The entire setup focuses on directing force exactly where the stone is already willing to separate. A crane-equipped vehicle approaches the marble face and aligns its arm with an existing fracture. The boom presses into the crack, applying steady outward force to widen the separation. The goal here isn't speed, but control. That push looks restrained, yet the stone clearly feels it. You can tell the pressure is being built deliberately, not dumped all at once. Nearby, a second vehicle delivers smaller stone blocks to the base of the fracture. These pieces are positioned carefully, stacked to create resistance and guidance for the next movement. Once set, the crane arm returns, pressing the main block toward the filled gap. That moment feels like loading tension into a spring made of rock. With pressure increasing, the marble block begins to tilt. The crane doesn't jerk or rush. It maintains a consistent push while gravity starts to assist. The inserted stones act as a pivot, redirecting force upward and outward. You'd never guess something this heavy could be persuaded instead of forced. That slow shift is where patience pays off the most. As the block reaches its tipping point, weight takes over. The stone leans, shifts, and drops onto the quarry floor in a controlled fall. Dust rises briefly, but the block lands intact, ready for further cutting. That drop feels decisive, like the quarry finally agreed to let go. This method avoids uncontrolled fractures and preserves usable material. Each vehicle plays a defined role, one shaping the brake, the other supporting it. Simple mechanics, but serious strength at work, proving that marble extraction here depends more on planning than impact. Size alone doesn't explain why the SCHE UERLE K-Mag K25 modular transporter changes how heavy cargo moves through ports like Dunkirk. This operation centers on transporting a 140-ton steel girder consignment using the K25 during its first deployment, handled by Capel Transport in October 2014. Positioning the load requires careful alignment as the modular platform distributes weight evenly across multiple axle lines.
I don't think I can take this anymore. I might just break. All the way hard and ache.
Steering corrections stay minimal while the transporter advances, keeping the steel girders stable over uneven port surfaces. Hydraulic suspension compensates continuously, maintaining level support as the route transitions between loading zones. That balance under load looks stronger than expected for something carrying this much steel. Load securing remains constant throughout the move, preventing shift or torsion as the convoy progresses. Coordination between operators and the transporter's control system ensures turning radii stay within tight port clearances. Feels like the machine already knows where the weight wants to go. As speed remains deliberately controlled, braking response stays predictable, even with the full payload engaged. The K25's modular design allows the configuration to adapt to the girder length without compromising maneuverability. That steel looks calm up there, almost like it forgot it weighs 140 tons. As the transport reaches its destination zone, final positioning relies on incremental steering inputs rather than broad corrections. This controlled approach protects both cargo and infrastructure, especially within active port traffic. The completed move confirms the K25's capability in real operating conditions, not test scenarios. Hard to imagine port traffic flowing smoothly if this wasn't dialed in so precisely. The result speaks through execution. One of Europe's heaviest first-run transports completed cleanly, efficiently, and without drama. Crews in jumbo derrick barges coordinate to discharge collapsed containers from a container vessel in Hong Kong waters. The operation focuses on unloading container units from a container vessel, relying on synchronized lifting rather than speed. Barges align alongside the ship, maintaining spacing while cranes position above the first container row. Rigging lines are secured, load balance checked, and lift paths confirmed before each move continues. Containers rise vertically, clearing the deck without swing, then shift laterally toward the barges. That lift looks heavier than expected, yet nothing drifts offline. Once lowered onto the barge deck, units are guided into place to prevent edge contact or stacking stress. Crews repeat the sequence methodically as container after container transitions from vessel to barge. Coordination between barge positioning and crane movement keeps traffic flow uninterrupted across the waterway. Operators adjust hoist speed to match wind and current, keeping the load predictable throughout the transfer. Feels like the whole setup already planned the next move before the current one finishes. As volume increases past the 100-unit mark, consistency becomes the real challenge. Structural checks continue visually, ensuring frames stay square during placement. That deck fills faster than you expect once the rhythm locks in. As the discharge nears completion, remaining containers are lifted with the same measured control, avoiding rushed final cycles. The barges gradually shift outward, clearing space for the last units. Final placement leaves each barge evenly loaded and ready for onward transport. Each completed lift reinforces trust between crews, equipment, and timing across the entire floating operation zone today now. Hard to picture this many containers moving smoothly without absolute coordination. More than 150 collapse containers leave the vessel efficiently, proving large-scale discharge can stay controlled, calm, and surprisingly clean even in busy Hong Kong waters. Five landing gear sets supporting 571 tons are replaced on an Airbus A380 at Emirates Engineering in Dubai. Hydraulic jacks lift the aircraft, wheels cleared in stages, sets removed and replaced over 14 days. That support load feels unreal, like swapping legs. High above ground, the WKBD antenna installation relies on steady control, not force. JP Jones and D7 Brian Bickneys coordinate the lift as the new repack antenna waits below, staged for a single clean placement on the tower. A construction helicopter approaches with the load suspended, keeping the antenna steady as wind and height test alignment. Ground crews manage clearances while the pilots hold position, matching speed and angle to the tower top. That hover looks calmer than expected at this altitude. As the antenna nears the mast, taglines guide rotation so mounting points line up without forcing contact. The helicopter eases forward, reducing sway while the team signals minor corrections. This setup feels like muscle and intelligence packed together. Bolts are readied, hands stay clear, and the load is lowered into place with measured control. Once seated, rigging is released and the helicopter backs away, leaving the antenna secured. Final connections lock the assembly to the structure, restoring broadcast capability after the repack work. That handoff from air to steel always feels decisive. Throughout the lift, communication stays constant between air and tower. The margin for error is slim, yet the sequence stays smooth from approach to release. You'd never think so much coordination could look this composed. With the antenna fixed atop the 1,000-foot tower, WKBD's upgrade stands complete, proof that careful planning beats raw force at height. Weather windows matter here, and timing keeps crews safe, while schedules stay intact today. Segmental beam formwork turns bridge construction into a controlled assembly task long before segments ever meet on site. Developed by Shandong Zibo Huanyu Bridge Formwork Company Limited, this precast segmental beam formwork system supports cantilever assembly with high repeatability and tight dimensional control. The system is built around a complete mold set consisting of bottom molds, side molds, end molds, and adjustable inner molds. That modular layout already hints at how many problems are solved before concrete is poured. Each casting station is equipped with 2 sets of bottom molds and working platforms, serving matching segments, freshly cast segments, and curing segments in rotation. Bottom mold trolleys move molds out, while gantry cranes handle positioning back into place. Vertical and horizontal hydraulic jacks mounted on the trolley allow fine adjustment of axis alignment and elevation. Those small corrections quietly decide whether the next segment will fit without debate. Side molds are mounted on support frames with screw adjustment rods and hinged rotation points. This allows controlled opening, closing, and dimensional tuning. To accommodate changing internal cavity sizes, the inner mold is designed as small combined units. Hydraulic systems drive vertical extension and lateral opening or closing, with dedicated trolleys handling insertion and removal. The movement looks simple, but every shift is doing structural math. The full formwork system delivers sufficient strength, stiffness, and stability. Smooth mold surfaces and sealed joints prevent slurry leakage, ensuring clean finishes and accurate geometry. Three-directional positioning reaches plus or minus 1 mm accuracy, enabling variation in segment length, cross-section, and both straight and curved beam production. That level of flexibility explains why this setup adapts so easily to different bridge layouts. During segment production, molds are positioned and adjusted to final dimensions before reinforcement cages are lifted into place. Concrete is poured and left to cure. Once strength is achieved, demolding follows a clear order. End molds, inner molds, then side molds. Seeing a finished segment released always feels like a quiet checkpoint. For the second segment, the first segment is used for match casting, ensuring precise alignment. The cycle repeats until all segments are completed. Nothing here relies on chance. Repetition does the heavy lifting. Highly complex geometry is produced without removing the part from the mill-turned CNC machine. This entire operation proves how multitasking machining replaces segmented workflows with continuous control. Working in a single setup directly reduces cumulative positioning error across multiple features. Raw material is clamped into the 250 mm chuck on the main spindle, where turning establishes the core shape and reference surfaces. With 29 kilowatts available at up to 5,000 RPM, the spindle maintains stable torque while cutting external diameters and internal bores. That steady engagement already shows this machine is built to commit, not hesitate. High spindle power allows consistent cutting parameters even during heavy material removal. Once primary turning is completed, the milling spindle enters the cycle without interrupting the setup. Driven by its own 29 kilowatts motor, it machines flats, pockets, and angled features directly on the rotating part. Axis coordination allows the tool to reach complex positions without shifting the workpiece. This feels like the machine refuses to break its focus once work begins. Multi-axis interpolation keeps tool engagement predictable across changing angles. Automatic tool changes keep the sequence moving as drilling, tapping, and contour milling follow. Each operation references the same datum, preventing alignment drift that often appears in multi-machine setups. You'd never expect this many features to stay this consistent in one fixture. Shared referencing helps maintain dimensional relationships between turned and milled surfaces. As machining progresses, the counter spindle moves into position. It synchronizes rotational speed with the main spindle before gripping the finished section of the part. The transfer occurs smoothly, allowing the main spindle to release without stopping the cycle. That handoff always looks like a quiet statement of control. Spindle synchronization ensures the part remains stable during transfer. With the component supported by the counterspindle, backside operations begin immediately. The milling spindle returns to machine rear-facing features, grooves, and profiles that would otherwise require a second setup. Somehow the workflow keeps moving as if the machine already knows what comes next. Backside machining in the same cycle removes the need for manual reorientation. Throughout the operation, coordinated motion between spindles and axes eliminates idle time. No reclamping, no manual repositioning, and no tolerance stacking appear along the way. This setup feels like muscle and logic working in the same direction. Cycle efficiency improves because machining and handling overlap within one program. By completing turning and milling in one uninterrupted sequence, the mill-turned CNC machine delivers a fully finished component in a single operation. This is where multitasking actually earns its name, reducing handling while maintaining control from the first cut to the last surface. Single-cycle completion shortens lead time while keeping process flow consistent. Small batch motor production often depends on machines that balance flexibility with repeatable results, and the semi-automatic armature winding machine from Nide Mechanical fits that space precisely. Designed around a double flyer winding system, this setup supports armatures used in mixer motors, DC motors, vacuum cleaner motors, and various power tool motors. The operator positions the armature and secures it before the flyers engage, setting winding paths without complex changeovers. Wire feeds smoothly as the flyers rotate, forming coils evenly around each slot. That consistency matters more than speed when output volumes stay modest. After each winding cycle, the armature is indexed manually to align the next section. This controlled pacing allows adjustments between models without stopping the entire line. Tension remains stable throughout, reducing uneven layering that could affect motor performance. You'd expect more fuss-switching motor types, but the workflow stays surprisingly calm. Once winding completes, the finished armature is removed for insulation and downstream assembly. The machine's layout keeps all key controls within reach, minimizing unnecessary movement during operation. That setup feels practical rather than overbuilt. For facilities with limited capacity needs, this semi-automatic approach keeps production manageable while maintaining coil accuracy. It supports multiple motor categories without heavy automation overhead, feels like a solid bridge between manual winding and fully automatic lines. The result is a machine that favors control, adaptability, and dependable output over sheer volume. The CONTESSI nozzle mixing torch delivers consistent cuts on steel thickness levels that challenge standard torches. Its sturdy body supports stable operation while dealing with very high thickness cuts. Gas mixing happens directly at the nozzle, allowing the flame to stay concentrated where the cut demands it. The operator adjusts the torch angle and flow to match material resistance, keeping the cut path steady. That flame control is the real backbone here. As cutting progresses, the torch maintains consistent energy delivery across dense sections. Slag separates cleanly as the cut advances, reducing rework on heavy plates. There's a moment when the torch pushes through thick steel, and you almost expect it to slow, but it doesn't. The robust design absorbs thermal stress without losing alignment. This is the kind of tool that feels built for long shifts, not quick demos. The result is reliable cutting performance on materials most torches struggle to handle. Pushing deeper cuts without sacrificing control is exactly what Coromil Plura heavy-duty end mills are built to handle. This video follows how a single 12mm tool is pushed through demanding roughing strategies while keeping cutting behavior predictable. That balance between depth and stability is where rough milling usually fails. Shoulder milling comes first, using the 2N34 21200 PC 1730 with 5 effective flutes. At 160 meters per minute and a depth of 24 millimeters, the cutter removes materials steadily while maintaining edge engagement. Consistent feed per tooth keeps load evenly distributed across the flutes. When depth shifts to 18 millimeters, speed drops slightly to preserve cutting conditions rather than forcing the tool. That adjustment shows how parameters guide performance, not brute force. The comparison tool follows the same paths under identical settings. Differences appear quickly as engagement increases. Tool behavior under load matters more than matching numbers on a chart. Shoulder milling continues with reduced radial engagement, preparing the workpiece for slotting. Full slot milling tests the cutter's ability to clear chips across the entire diameter. Fine and coarse strategies alternate, with feed per tooth adjusted to keep chip formation stable. Slotting always exposes weak geometry, and this is where design choices show up fast. Ramping at 7 degrees pushes axial load deeper into the cut. The Plura tool maintains control through 16.8 millimeters depth while holding steady feed. This part feels tense, like the tool is being quietly challenged. Helical interpolation follows, opening pockets smoothly without abrupt direction changes. Finally, full slot cutting at twice the diameter depth closes the sequence. The result highlights how one tool manages varied operations without breaking flow. Seeing one cutter handle this range without drama is genuinely surprising. Steel forging on this scale depends on coordination across continents, and Befrungi's network shows how heavy parts are shaped through controlled force rather than speed. From its European roots to facilities in the US and UK, the group focuses on hot-forming components for demanding industries. At BIFRANGI SPA, vast forging areas support presses ranging from 2,500 to 8,000 tons, alongside the BF 4000 horizontal forging press, rated at 4,000 tons. Steel bars up to 25 centimeters in diameter are heated and positioned for vertical and horizontal forming. Those dimensions already hint at how serious the loads are. Material handling flows toward high automation presses, where force is applied in measured strokes instead of sudden impact. Induction hardening follows selected forming steps, improving surface durability where components face repeated stress. This is strength being built layer by layer, not rushed into shape. Across Europe, Befrangi GmbH in Alphafen, Austria continues similar operations with presses adapted to different geometries. In the United States, Boltex Manufacturing Forge in Houston expands that capability. The forging facility processes up to 5,000 tons per month, producing parts weighing from 1 pound up to 11,000 pounds. The DG140H counterblow hammer delivers forming energy up to 1,400 kilojoules, while hydraulic forging presses rated at 12,000 and 5,000 tons handle large closed die components. When opposing forces meet inside a counterblow hammer, the metal has no choice but to comply. Trimmer presses refine edges, keeping parts within strict dimensional targets. There's a moment when the scale stops being numbers and starts feeling physical. Machining follows forging at Boltex Manufacturing in Houston, where up to 200,000 parts per month are finished. Large turning and milling systems accommodate diameters up to 88 inches, converting forged blanks into ready-to-assemble components. In the UK, Befrange's Lincoln forging plants rely on 16,000 and 32,000 ton screw presses, producing forgings up to 1,000 kilos and 3 meters long. Mass and geometric centering, along with magnetic particle inspection, ensure internal integrity before parts move forward. That inspection step quietly decides whether weeks of work move on or stop cold. Final machining at Sheffield focuses on crankshaft production, combining forming knowledge with tight dimensional control across all sites. Planning drives the outcome more than spectacle. It's not about one giant press, but how every station hands off to the next without losing intent. Steel bars are processed, cut, and directed into bins using the RMS Rebar shear line with 611 shear. In this setup, straight rebar is guided into a continuous system designed to cut, sort, and stage material with minimal interruption. That kind of flow is what keeps fabrication floors predictable instead of reactive. Bars enter the pass line and are aligned before reaching the shear. The 611 shear delivers clean cuts while maintaining consistent length accuracy across repeated cycles. Cut quality matters here because every downstream bundle depends on it. Immediately after shearing, kickoff arms activate to direct bars toward the correct bin. Their spacing and force ensure material clears the line without hesitation. Those arms don't rush, but they never pause either. Bins are positioned to store multiple lengths efficiently. A higher pass line angle helps bars slide naturally into place, reducing the chance of hang-ups. You can feel how gravity is quietly doing part of the work. Short bars are handled through a dedicated short bar shearing section, limiting manual handling and keeping operators out of repetitive tasks. That alone changes the pace of the floor. Upstream, the preload table allows 2 loads of steel to be staged while the line keeps running. Independent controls give operators flexibility without stopping production. It's one of those features that saves time without calling attention to itself. Across a cycle, modular components support steady throughput and long-term use. The whole line feels less like a machine and more like a routine that just keeps going. Large-capacity Pavali containers are built through a coordinated metal forming line at Yashwant Industries in Ahmedabad, where sheet steel is guided step by step rather than rushed into shape. The sequence opens with a shearing machine cutting flat sheets to controlled sizes, keeping edges straight for later joining. That first cut quietly decides how clean everything downstream can be. The blanks then move to sheet bending machines, where angles are formed to define the container wall profile without stressing the material too early. Formed sections are aligned for longitudinal argon welding. The welding machine runs a steady seam along the length, joining panels into a continuous shell. Heat input is balanced to keep distortion low while maintaining joint strength. A single uninterrupted weld line carries a lot of responsibility here. Once joined, the shell passes through a skin pass roller machine that smooths the surface and evens thickness, preparing it for shaping. That rolling step feels like ironing metal instead of fabric. Shaping continues with mechanical GOT machines and spinning machines that gradually push the cylindrical body toward its final geometry. Instead of forcing the steel all at once, pressure builds in stages, allowing the wall to stretch evenly. For deeper forms, hydraulic GOT machines and hydraulic deep draw press machines take over, applying controlled force to pull the base and corners into place. When the press settles in, the steel stops arguing and starts cooperating. The spinning machine refines roundness, ensuring the container sits stable during use. After forming, surfaces are refined using a buffing motor. This removes minor marks left from shaping and prepares the exterior for finishing. The silver touch machine follows, enhancing appearance while adding a protective layer suited for storage environments. That finish is where industrial work suddenly looks presentable. Throughout the line, components are repositioned by hand and machine, maintaining alignment without breaking flow. There's a calm confidence in how each station hands off to the next. Final inspection checks geometry, weld continuity, and surface condition before containers are cleared for storage applications. These Pavali units are designed for durability rather than display, built to hold goods reliably in demanding conditions. Yashwan Industries limits emphasis on branding here, letting process consistency speak instead. Once stacked and ready, the containers feel less like products and more like tools waiting for work. The result is a practical storage solution shaped by sequence, pressure control, and steady repetition rather than dramatic force. 23,000 tons of hardware come together inside the tokamak pit. The cryostat base and lower cylinder already anchor the structure, forming the foundation that supports every layer above. That scale alone changes how you think about assembly work. Gravity supports for the toroidal field follow, transferring massive loads safely into the base. Thermal shields are positioned next, enclosing the lower cryostat to manage heat exchange before major magnetic systems arrive. Nothing moves forward here unless the previous layer holds its ground. Pre-compression rings and the bottom cylinder lock the structure, preparing it to receive poloidal field coils and correction coil feeder rings. As the central column rises, radial beams guide the placement of vacuum vessel sectors, each aligned with extreme care across the pit. Upper port stub extensions expand access points, followed by the removal of temporary supports. Side and top correction coils then surround the core, leading to installation of the central solenoid. At this point, the machine finally starts to feel complete. Cold steel changes character fast when the Hebo Money Machine 2 enters the workflow, turning straight bar into decorative iron through controlled force instead of heat. The main motor unit drives a modular setup where attachments rotate in and out without slowing production. Twisting begins with the Hebo twisting and drive attachment, pulling bars up to 1.25 inches into clean spirals. That steady rotation feels more like guiding than forcing. Next, the end forging attachment shapes smooth tapers, fishtails, and spearheads. Material is compressed evenly, keeping symmetry consistent across batches. Seeing identical tapers appear seconds apart is a quiet flex. Scroll work follows on the Hebo scroll machine, forming tight curves cold, even on thicker stock. Circles and scrolls emerge quickly, sized on demand rather than guessed. The basket attachment adds hammered filaments and collars, combining strands into ornamental bundles. This is where straight bar suddenly looks handcrafted. For pressing tasks, the hydraulic table applies up to 24 tons, bending metal cold and punching belly pickets at speed. One day, hundreds of pickets. Wait, what? Embossing and texturing attachments finish the surface, hammering tubing and marking long bars in seconds. Across the line, each station feeds the next, with minimal reset. The Hebo system favors repeatability and pace, proving ornamental iron doesn't need slow steps to feel deliberate. 14 strands of copper move in parallel as the automatic BLDC motor winding machine applies needle winding technology to stator production. Instead of relying on single wire passes, this system drives multiple wires through narrow slots in one coordinated motion. That alone explains why output climbs without rushing the cycle. Stator cores are manually loaded, then clamped automatically as the machine locks alignment before winding begins. Needle heads guide each strand precisely into the slots, maintaining even distribution across the stator. Turn counts and slot numbers are defined through the HMI, allowing fast changeovers without mechanical adjustment. This setup feels built for repeatability rather than constant tweaking. As winding continues, wire tension remains stable across all 14 strands. The machine handles parallel routing smoothly, avoiding overlap or crowding inside the slots. Once target turns are reached, wire clamping and cutting occur without stopping the sequence. Seeing 14 strands finished together is oddly reassuring. Multi-tapping capability expands coil configurations, supporting different BLDC motor designs on the same platform. Throughout the cycle, the machine monitors its own operation, enabling remote diagnostics when needed. That kind of self-checking quietly saves time later. After winding, the completed stator is released for unloading, ready for insulation and downstream assembly. No rethreading, no manual corrections, just consistent coils leaving the station. This is one of those machines that doesn't ask for attention once it's set. By combining needle winding with multi-strand control, the BLDC winding machine delivers stable, high-speed stator production. Hard to ignore how smoothly everything stays on track. Axial force reshapes a 150-ton disc on the 10,000-ton forging press at Sheffield Forgemasters, compressing a disc forging toward final density. That pressure commitment matters. The press holds, releases, repeats. No pauses, just force applied exactly once under controlled conditions.